Okay, so today we are going through 10.5 and 10.6. So 10.5 talks about using some properties of logs, and then 10.6 talks about natural logs, which I love. So first, 10.5, part one, using the product property. So this is a really kind of interesting property of logarithms that says that if x, y, and b are positive real numbers and b does not equal 1, then log base b of x times y, so again, x and y are just representing numbers. You can split that up into actually addition. So multiplication of x times y is equal to log base b of x plus log base b of y. And you can do this vice versa as well. If you have log base b of x plus log base b of y, you can consolidate that into one logarithm, log base b of x times y. So for example, we have log base 3 of 1/2 plus log base 3 of 12. And then again, we have log base b. In this case, our b is 3, log base b of 3 of 1/2 plus log base 3 of 12. So that's the same thing as log base b of x plus log base b of y. And we know that that is equal to log base b of x times y. So we can rewrite our expression as log base 3 of 1/2 times 12, which we know is in fact 6. So our final answer is going to be log base 3 of 6. So log base 3 of 1/2 plus log base 3 of 12 is log base b of log base 3 of 6. And you can actually check that with your calculator and see that it does in fact work out. So for these types of problems and for all the other properties we are doing as well, you will be asked to go ahead and either consolidate into one logarithm like we just did, or perhaps break it up. Actually, no, you won't be asked to break it up. You'd normally be asked to consolidate into one logarithm like we just did. All right, part 2, the quotient property. So this is the same thing, but it's saying that when you have log base b of x minus log base b of y, that is the same thing as division, in fact. So let's look at our example. We have log base 10 of 27 minus log base 10 of 3. So we do in fact have log base b of x minus log base b of y. In this case, our base is 10, our x is 27, and our y is 3. And so we know that that is the same thing as log base 10 of 27 divided by 3, which we know is log base 10 of 9. And so log base 10 of 27 minus log base 10 of 3 is equal to log base 10 of 9. Okay, so again, super similar to the product property, but this time we are dividing. All right, next up we have the power property. So if x, y, and b are positive real numbers and b does not equal 1, then when we have log base b of x to the r, so we have some number x raised to some power r, you can actually bring that power r to the front of your log and then leave your log as is. Okay, so for instance, when we have log base 5 of x cubed, we can take that power and bring it up to the front, and we know that this is equal to 3 times log base 5 of x. Okay, so you can kind of bring that power down to the front and then leave your log as is, and that is the power property. And then part 4 of 10.5 is using these properties together. So for example, number 1 and 2, we are asked to write as a single logarithm. So we have 2 log base 5 of 3 plus 3 log base 5 of 2, okay? And so what we are going to do is first apply the power property, right? So this is the one property that we might sometimes use backwards, right? So we have r, some constant, times log base b of x, and we know that we can actually just bring that to the front for a power. So we could write this as log base 5 of 3 squared, again, doing the opposite. Instead of bringing that power out in front, we're putting it back into the power, plus log base 5 of 2 cubed. Okay, and then we know that that is going to be log base 5 of 9 plus log base 5 of 8. Okay, and then we are going to use our product property because we see that we have addition. So we're going to have log base 5 of 9 times 8, which is equal to 72. So we're going to get our final answer is log base 5 of 72. And we have successfully written our starting expression as a single logarithm, just like we were asked. All right, next up we have log base 4 of 25 plus log base 4 of 3 minus log base 4 of 5. Okay, so the first thing we're going to do is apply the product property to our first two logarithmic expressions. And we know that log base 4 of 25 plus log base 4 of 3 is the same thing as log base 4 of 25 times 3 minus log base 4 of 5. 25 times 3 is, of course, 75. So we'll have log base 4 75 minus log base 4 of 5. And then we are going to use our quotient property, which says that when we have subtraction, we know that that's going to be equal to log base 4 of 75 divided by 5. And 75 divided by 5 is, in fact, of course, 15. So we'll have log base 4. I wrote a 5. Log base 4 of 15. And that, my friends, is 10.5. So these logarithmic properties are not too complicated, but you will have to kind of get used to using them just because they're kind of this completely new idea. So make sure you are practicing that. And now we are to 10.6. So part 1 is approximating common logarithms. So the definition of a common logarithm is a logarithm of base 10. So that's a common log. And because our number system is a base 10 decimal system, that's kind of where that like 10 is common thing comes from. So when you just see log of x, that is an implied base of 10. So unless you have a base that is specifically not or specifically labeled, you'll just see log of something. And again, that 10 is implied to be there. Okay, so when you just see log, know in your head that's log base 10. Okay, so again, in other words, if there's no base b that is specified, it is implied that the base is 10. So like in your calculator, you probably have a log button and it probably doesn't allow you to specify the base. So on your calculator, you know, okay, base 10. I'm trying to find my log button. I see natural log, but we'll get there. So in other words, if there's no base b, it's implied that the base is 10. So example, use a calculator to approximate log 7 to 4 decimal places. So really all you need to do here is turn on your calculator and then find wherever your log button is. If you cannot find it, I would recommend that you Google it for your calculator and it will show you where it is. I need to Google it for my calculator, but I just found it actually. So it says log, and then I'm just going to type log of 7, close parentheses, equals, and then it gives me a nice little decimal, and I want that to be approximated to 4 decimal places, and so I could say log 7 is approximately equal to 0.8451, which is what you should get when you type that into your calculator. So approximating logs using your calculator, pretty easy. All right, part 2, approximating natural logs. Natural logs are also frequently used, especially to describe natural events, hence the name, which I actually didn't know until I read that in the textbook, and I was like, oh, interesting. Natural logs are logs that have the base e, which is a constant that is approximately equal to 2.7183. So e is kind of this weird thing, kind of like pi, where it's just like this irrational number that we give a letter to. So a natural log, we say as ln of x, and that's literally the way you say it, like ln, natural log. And that is log base e of x. So ln of x is equal to log base e of x. But again, you won't ever see like log base e of x. It's ln x. Okay, and that is natural log. So then use a calculator to approximate ln of 8 to 4 decimal places. So this comes down to finding the ln button on your calculator. See, so it'll just say like ln of 8 is approximately equal to 2.0795. So I got ln of 8 is approximately equal to, where are we? I got 2.0795. So that's 2.0795. Okay. So, I lied, it's 9.4. I rounded wrong. Anyway, all right, part 3, evaluating natural logs of powers of e. So as a result of the property log b of e to the x equals x, we know that log e of e to the x equals x, or in other words, natural log e to the x is equal to x. So this is an important one, ln of e to the x equals x. This is just saying that essentially natural log and e cancel each other, right? Because then we get x equals x. So that is an important property that you should know. So I'm gonna circle that guy. And then note that ln of e to the 1 is equal to 1, or in other words, ln of e is equal to 1. Okay. So example, solve the natural log of 3x equals 5. ln of 3x equals 5. Give an exact solution and then approximate your solution to 4 decimal places. So remember that the base of a natural log is understood to be e, right? So we can think about this as like log base e of 3x equals 5, in which case we can use our little circle method to rewrite this as e to the 5 is equal to 3x. And then again, we're solving for x, so I'm going to divide by 3. And I'm going to get e to the 5th over 3 is equal to x. And then you could type that into your calculator because you definitely have a button for e somewhere. Mine is right next to ln, but if you need help finding these on your calculator, just Google it or come to tutorial and I will Google it and show you the results. E to the 5th divided by 3 is approximately equal to, I got a value of 49.4711 approximately. Or 49.4711. Is that what I said? 49.4711, which is e to the 5th over 3. So I gave an exact answer, which is this guy right here, no decimal approximation, and then I approximated as well. Okay. So recall our formula A equals P times 1 plus R over N to the NT for compound interest, where N is the number of compoundings per year. A equals PE to the RT is a formula for when interest is compounded continuously, where R is the interest rate and interest is compounded continuously for T years. So for example, find the amount owed at the end of 5 years if $1,600 is loaned at a rate of 9% compounded continuously. So whenever you see the word compounded continuously, you should know A equals PE to the RT. And I will give you like this equation and this equation on the test, but I'm not going to tell you which one is which. So you need to know that PE to the RT is compounded continuously, and the other one is compound interest. Okay, so make a mental note of that. And then let's do our example. So the amount owed at the end of 5 years, if 1,600, so A is going to be the amount accrued, right, equals P, which is the size of the loan. So we can say that for this problem, the size of the loan is $1,600. E to the R is the rate of interest, which in this case is 9.09 times T, 5 years. And then A is going to be equal to simply whatever you get when you plug this into your calculator. Great type of calculator problem that might be on your chapter 10 test. So I'm going to type in 1,600 times E to the power of 0.09 times 5. And I'm going to get A is approximately equal to, let me make my little equal signs wiggly because it is not exactly equal to, it is approximately equal to, eraser, go ahead and say that A is approximately equal to, I got 2509.3, but this is dollars, so that's going to be 30 cents, and I'm going to put a little dollar sign there. Okay, so these compounded continuously problems are a little bit easier. There's a lot less to kind of enter in your calculator, a little bit less room for error there. Okay, and then last up, we have change of base formula. So calculators are great tools for approximating logs and natural logs. Unfortunately, some calculators cannot be used to approximate logs with bases other than E or 10. In such cases, we use this convenient thing called the change in base formula. Okay, so if you need to approximate some log on your calculator, but you are not able to change the base in your actual calculator, I think the fancier TI-84s can do this, maybe, but maybe the older ones can't, or the fancier ones can change the base, but the older ones can't. I don't know. Either way, this formula is super easy to use. And so this says that log B of A is equal to log C of A divided by log C of B. Okay, and so this will allow you to approximate literally any log on your calculator. So like if we wanted to approximate log base 5 of 3, then what you're going to do is use the change of base to write log base 5 of 3 as the quotient of 2 logs with base 10, right? So we see that when we kind of change our log to a quotient, they have the same base, C, and so we're going to use this property to change log base 5 of 3 to be equal to log base 10 of A, which in this case is 3. So we're going to have log base 10 of 3 divided by log base 10 of B, which in this case is in fact 5. So I would type in my calculator log 3 divided by log 5, and that is going to be equal to approximately 0.6826. Okay, and so if you can change the base in your calculator, then you would just type in log base 5 of 3, but if you cannot, you change it to log 3 divided by log 5. Super easy to use. All you have to do is remember, okay, like log of that guy divided by log of your base, and that is the change of base formula. So super convenient for older calculators. Yeah, so that is change of base. That's all for 10.5 and 10.6. Thanks for watching, guys. Have a lovely day.